Acid-base titration. Titration is a technique to determine the concentration of an unknown solution. It is a quantitative process of adding a known quantity of a liquid aqueous solution, called the titrant, to a measured sample, analyte, to react in a definite known proportion. The addition of the substance is stopped when the equivalence point is reached. That is determined by a color change, when a point is reached when one reactant is fully consumed. The fixed volume of the analyte is measured using a pipette into the flask. Right? The pipette pours the analyte in there. The titrant is added from the buret slowly. The indicator drops added to the flask will indicate the end point of titration when the analyte is completely reacted with the titrant from the buret. The volume of the titrant required can be directly read from the buret. See, you got all these marks there? It is important to accurately read the starting and ending amounts of liquid in the buret when doing a titration. The surface tension of a liquid causes the liquid in a container, including a buret, to curve up, this here, call that convex, or down, concave. That's called a meniscus. Either way, when reading a meniscus, read from the center of the liquid, either the top of the upward bulge or the bottom of the downward bulge. In acid-base titrations, a few drops of an indicator, usually an organic acid that can change color in acid and base medium, will be used. The indicator will be added to the analyte in the flask prior to the titration. That indicator provides the color change that marks the endpoint. With strong acids or bases, a commonly used indicator is phenolphthalein. It is pink when the pH is 8.2 or higher. In titration, it is best to obtain the lightest stable shade of pink. It is added to the analyte prior to titration. First, the buret is rinsed with the titrant and then filled with the titrant. Remove any air bubbles from the stop valve by draining a few drops so that the tip of the buret is also filled with the titrant. The pipette is then rinsed with the analyte, then pipette the analyte and transfer into the flask. The titrant is added slowly to the analyte. The end point is reached when the first permanent color change takes place. At the end point, the balanced equation will determine the relationship between the number of moles of titrant and analyte. With monoprotic acids and bases, which we will use in all our problems in this course, the moles of the titrant are equal to the moles of the analyte in the flask. Once you know the moles and volumes of the analyte and titrant, determine their concentration is pretty straightforward. For monoprotic acids and bases, use M1V1 equals M2V2 to determine the unknown concentration of the analyte or titrant, where M is the molar concentration and V is the volume. Multiplying M, which is moles per unit volume, by volume, which is the volume, yields the moles of reactant. A 25 milliliter sample of 0.225 molar nitric acid is titrated with 0.500 molar sodium hydroxide. What volume of sodium hydroxide will be required to reach the equivalence point? We use our general formula here, M1V1 equals M2V2, and then we solve for the unknown, which is V2, which is the volume of the sodium hydroxide, right over here. We then plug in our givens, do the math, and we get 11.3 milliliters. Please note that unit conversions are not necessary as long as the units of the known quantities agree, since they will cancel out in the equation. A student makes 1 liter of hydrochloric acid solution for an experiment which requires to have a molarity of 0.200 molar. The student standardizes the solution by titrating a 45 milliliter sample of the hydrochloric acid solution to its endpoint, with 15.9 milliliters of 0.500 molar sodium hydroxide. What is the actual molarity of the solution that the student made? Did the student make the solution accurately? And here's our reaction. We start with our formula, and M1V1, that's going to represent the hydrochloric acid, and M2V2 is a sodium hydroxide. So we isolate M1 by dividing both sides by V1. We then put in our givens. And right here, this is for sodium hydroxide. That's the molarity and the volume. And here's the hydrochloric acid. And then we calculate a molarity. The student actually got a molarity of 0.177 molar. The student wanted 0.200. That's not close enough. You should be over 0.19, somewhere between 0.19 and 2.1. 0.21 would be a lot better. So we're going to say, nope, not made accurately. A student performs a titration and finds that it takes 18.7 milliliters of titrant to reach the endpoint. However, the student calculated that it would take 24.3 milliliters to reach the endpoint. Which of the following would account for the error? Let's see. 1. The student neglected to take into account that the titrant reading did not start at 0. The student neglected to remove the air bubbles from the Buret. The student overshot the endpoint and did not stop as soon as the color became permanent. Or the student stopped the titration at the first sign of color and did not check to see if that color was permanent. Number 4 is the correct answer. The other 3 answers would cause the measured amount of titrant to be larger than the calculated value. And our measured amount of titrate, or the student's measured amount of titrant, is less than the calculated value.